Okay, welcome everyone to What's a Microcontroller with Python and the Microbit. This is day one of the workshop. With you today are me, Andy, Ari Alvarez, and Stephanie, whom, sorry, she didn't make the list. There we go. And here is the slides. I'm going to paste this into the workshop chat. Whoa. Didn't mean to do that. Okay, let's try again. Copy, and then find the chat, and then paste. Okay, so this slideshow is going to be really useful as a link repository for you. It will have most, if not all, of the links that you'll see used during the workshop. Again, with you today, Andy, that's me on the left, Ari Alvarez in the center, and Stephanie Lindsay on the right. And I'd like to take care of a few things while I'm talking about just some preliminary stuff before we jump into the hands-on. What I'd like to do is have everyone get their video set up so that they can work on a separate screen. So here is an example of what it might look like when you're done if you have one screen. If you have two, organize it in whatever way you think is going to be most effective for you. If you have one screen, what I suggest is to go to the upper right in your Zoom and you'll see a little view icon. And you can click that and select Exit Full Screen. And once you've exited full screen, you'll have a window. And as an example here, I've resized it on the left. And then if everybody would also open a Chrome browser and go to python.microbit.org/v/2, I'll go ahead and paste that in to the copy and paste. So there's a link to python.microbit.org/v/2. We can use v3, but since the tutorials have full support for v2 right now, and there would be a lot to replace, we're delaying that. Hopefully, we're hoping to do that this summer to get up to speed with the v3. It is a nicer editor. There's no actual problems with v2 though, so we're going to keep it since it's in lockstep with the tutorials for now.
Andy, have you heard of any problems using the microbit.org editor with Microsoft Edge?
No. Well, I mean, it wasn't possible until a very short while ago, but it should work. And if it doesn't work, then Chrome would be Chrome browser would be your other alternative. But Microsoft Edge, as long as it's an updated browser, it should work just fine. Unless there's some kind of district policy that is preventing Web Serial from being used in the Edge editor. It's been working fine.
Thank you.
I'll be using Chrome. Anyway, so resize if you have a single screen, resize your Zoom window so that you can kind of look at what's going on and then also have an editor open. Again, if you have two screens, just do whatever's most efficient for you. Let's see, do we have anything seem to work in Edge for me? Oh, thank you, Nilu. Let's see. Yeah. So yeah, it's worked in Edge for me too. I have not stress tested it, so please let me know if anything seems out of order. The other thing I'd like you to do while I'm speaking, before we get to the hands-on, is to connect your microbit to the to your USB cable and then connect your USB cable to your computer. And wow, this is really, I'm going to have to maybe freeze the autofocus. We'll keep an eye on that as we go through the workshop. All right, a little bit more about me. My background is in electronics, electronics engineering. I've been writing educational textbooks for the last 20 years, along with doing some product development and most recently, of course, web textbooks and focusing on the microbit. We've got the Cyberbot robot here, and then the What's a Microcontroller, and I've also been doing some cybersecurity material, which is available for both the Cyberbot and the microbit on its own, depending on how depending on what you have. Certainly the Cyberbot adds a more physical attribute to cybersecurity, whereas the microbit on its own is a little bit more, feels a little bit more virtual. But both have quite a bit of material available in cybersecurity, as well as what we'll be talking about today, which is electronics, and then the Cyberbot robot. For those of you who are new to Parallax, we are a small 20-employee company just outside of Sacramento, California, on your way to Lake Tahoe. We're kind of between San Francisco and Lake Tahoe in the center of the state. And we've been doing educational materials since 1997, and the business started back in 1988. The main focus at Parallax has been electronics, and especially the microcontroller brains that are programmed and then put into products. So if it's something like that has push buttons and a little display and makes speaker tones, chances are it's got a microcontroller in it, which has a program we call firmware that does stuff like listen for an electrical change on the microwave oven's keypad, and then send that rapid signal to the speaker, the rapid high-low signal to make the speaker vibrate so we hear a beep, and all the other things that a product does. But we're also interested in rapid prototyping and inventing, and so these examples down here all have Parallax microcontrollers in them. Chip Gracie is Parallax chief inventor. He's designed a number of very popular microcontrollers, which I'll talk about in a second. And then Ken, his brother, is in charge of marketing, and he's our CEO. So this guy on the left, Chip, his big splash in the microcontroller world was the basic stamp back in the late 90s. This pretty much took microcontroller hobby and education and literally transformed it from something that took a very technical background and some or at least some technical education, and it changed it to something pretty much anybody could plug this thing in and connect a circuit to it and write a short program and have an actual application working. It became popular, even more popular, when we added it to the Bobot robot that you see here. Since then, we've gone through a number of versions of introduction to electronics, be it with the propeller microcontroller, the Arduino microcontroller, and then most recently the microbit microcontroller, which is it's been very popular. It started out with a big splash because the British Broadcasting Corporation, the BBC, they had over 1 million of these manufactured and gave them to all of the middle school students in Great Britain, and along with some curriculum that they could try out. And so what I'd like to do as a warm-up exercise here is try out some of the things from the most basic microbit introduction. And what this is it's a set of introductions where you can, a student can go and they can follow a link, and when they do that, they'll get to see a some videos about how it works. And then they'll have the option of doing the code in either make code, that's a block-based code, or Python. And so I'll go ahead and paste you some code in a second. I just want to emphasize that this is a great starting place and an icebreaker. And there's a lot of projects here that students will find particularly engaging. And in the classroom situation, I know not all of you are going to have more than one microbit, but in the classroom situation, one of the things that's really fun is these things have built-in radios, as well as a compass and a tilt sensing accelerometer, a microphone, a speaker, buttons, and a little display. So it's kind of like a microcosm of a cell phone. And I'm looking for radio. So like if we were to filter by radio in the classroom, you have all these multi-microbit projects that students can pair up or even get into small groups to do. And thought I'd mention that. But since we only have one microbit for sure, today, what I'll do as an icebreaker is the step counter. And so I'll go ahead and paste in the code into your chat. That's going to be the Python code. So you've got these tabs up here. So you've got your choice of either make code, blocks, or Python. And so this is a little bit further down in the things to try. The way they've organized it is so that, at the very beginning, you're just displaying a message. And then later on, let's see if I can get back to the main page here. So we start with a static display, then a repeating display, some animation. And as we go down, we add in more things. Didn't mean to do that. They add in more things in terms of programming concepts. And so there's kind of an organic learning experience as the students go through this. And let's see. So I was going to paste in the, okay, so there, I just pasted in the code from the step counter, which is right here. I'll also paste in a link to it, just so you can see where it came from. And then a link to the main Make It Code It site, which is also in the slides, but just in case you wanted to go and take a quick peek at all these little activities that students can try. And let's see here. And then I need to go back and get the step counter code and paste it into my editor. And so what you can do is you can basically, if you want to paste something from the chat into your editor, you can hit Control-A, and that'll select all of your text, and then Control-V, and that'll paste over having selected it all with the with whatever you got from the chat, or if you copied and pasted from a web page, it also works there. So then, as we did in the homework, we'll need to connect to our microbit and then flash. But we won't need to open serial because this is using display.show. There's no print statements in here. If you see print statements in here, then you can go to the serial terminal and you will see some things printed. This was from a previous program I had running. All right, so I'll close that. So again, you'll want to hit connect, then flash, and then nothing will show on your microbit, at least not immediately. And but if you give it a shake, nothing happens. There we go. So that's one step, 2 steps, 3 steps, and so on. And so there's your step counter, and they've got some additional activities to adjust its sensitivity and other cool stuff. Okay, why is it that you don't serial when it is display rather than print? Okay. I'm not sure what the question means. It's just there are basically two different ways to do this. One is using the built-in microbit display. And I could, in addition, for example, say print, and then like maybe in quotes, steps equals, and then the value of the steps variable. And if I rerun it, now it'll both print to the serial terminal and to the display here. So if I shake it, you'll see it in the display on the microbit, and then you'll also see it in the serial terminal. Let's see here.
Reply is, okay, I see what you mean, got it.
Excellent. Yes, and these are great questions. Please keep them coming, folks. Thank you. Let's see. So I wanted you to be aware of this resource. Again, it's microbit.org/project/make-it-coded. And it's something you can do with the microbit on its own before getting started with the electronics stuff. There is more like this in a getting started with the microbit for middle school teachers Zoom workshop that the Granite School District had us do, and magnanimously shared it with everybody out in the world. So these are the two YouTube links. I think the majority of the good stuff is in the first, it's either an hour and a half or a 2-hour workshop. And then there's also a link to the slideshow for that right there. And you all have my email, so please feel free to also reach out if you're looking at any of these resources and questions come up. Okay, so for this week, on Monday, we'll look over the homework, we'll put together the breadboard kit, and then we'll hopefully build a couple circuits. Otherwise, those will end up being homework. On Wednesday, I'm hoping to get through build and test a light actually today. We'll see how it goes. Then we'll do some circuit measurements, and we'll also do some applications, those being lights that you build on a breadboard and push buttons built on a breadboard to kind of take a closer look at what's built into the microbit and how it works. Along the way, we'll learn about analog to digital conversion. We'll learn about high and low states and some computer science concepts, timing, percent duty. There's a lot of good stuff in here. This, by the way, is it was intended to be a pre-engineering curriculum. And so there's more concepts than just gee whiz. There's some, well, you'll see there's some real electronics concepts that any of you who have studied it will find to be familiar. For the homework on Wednesday, we'll add a servo and a potentiometer. And then on Friday, we'll experiment with those, and we'll also look over the teaching materials and some of the related kits. I'll talk about those briefly today also. Okay, so here is what came in your box. Lots of electronics parts and electronic prototyping breadboard and an adapter to connect your microbit to the breadboard. When you do so, and if you really go nuts with your circuits, it might look something like this with all the potentiometer, light sensor, push buttons. We actually don't have a speaker in the kit. There is a speaker on the back of the microbit, though. We've got a servo. The battery pack is needed for the servo. Otherwise, you can leave the battery pack unplugged. Let's see, LED lights and push buttons. So that's an example. And there's lots more parts in the kit for extending some electronics projects. One of the reasons this is going to be important is we already have some workforce development issues in the country where it's come up on the news. I'm sure you've seen it about reshoring integrated circuit manufacturing and manufacturing and production more generally. And so there will be increasing opportunities electronics is an example of one of the things that will become more valuable. And so it's very worthwhile. I think it's a very worthwhile introduction for students. So this is a lot of blah, blah, blah. Go ahead and read it. I think I'll try to make, well, I've already spoken about most of what's here actually, except for that, that it's estimated as a 40-hour class at this point. Okay, so let's talk about student and educator resources. These are at learn.parallax.com. I'll go ahead and paste that link into you. And no need to follow this per se. If you just want to look on, that's fine. This homepage is where all of the student online textbook links live. And so we've got a whole bunch of robots, cybersecurity, different flavors of robots with the Arduino, the basic stamp, the propeller microcontroller, and then down here we can see the Cyberbot robot, which is a really cool little robot that looks like this. Let's see here. Looks something like this. And so it has a similar adapter where the microbit is plugged in, and lots of circuits are built on here to help the robot be autonomous. And we also make use of the radio features and the built-in compass and accelerometer and all the other goodies that the microbit has. And then what we'll be talking about today is the what's a microcontroller with Python and the microbit. So this is the electronics textbook right here. Electricity and electronics, pasting that into the chat. Now we have some prerequisites, which is basically connecting your microbit, how to save a script in the version 2 editor, how to write microbit programs. So these two were in the actually all three of these were either part of the homework or were kind of summarized by the homework. And so I'll talk a little bit about these more in a minute. Computer microbit talk is fun. And again, that was sort of folded into a shorter version of the homework that we all did. Again, coming up in a later slide. Then the main lessons are setting up and testing the breadboard system, taking electrical measurements, and then we have lights, push buttons, servo control, and then also on Friday we'll be experimenting with the potentiometer as well. And that is coming soon. It will be inside a draft document, but it is coming soon to this page as well. And let's see, did I remember to paste that into copy? Ooh, somebody has put legs on their Cyberbot. That's pretty cool. Carol, if you'd like to email me a photo, I'll share that at possibly next workshop or on Friday.
She was showing it in the camera.
Oh, cool. Do you want me to switch over to her or?
Oh, later, just in case.
Okay. All right. Now, the other thing about learn.parallax.com,
I'll send you a video of it, Andy.
Oh, thank you. Yeah, we'll go ahead and play that as time permits. So going back to learn.parallax.com. So I'm back on the home page where all of these are textbooks for student tutorials. There's also an educators link. And when you follow that, then we can go to, where did it go? There it is. What's a microcontroller resources? Oh no, that's for the basic stamp. Uh-oh.
What are you looking for, Andy?
The electronics with the, here it is. What's a microcontroller with Python? I passed it up. All right, so here we are. So this is the educators resources, and there's some publicly available links here, but for assessment material, you have to log in. And so, so I'll go ahead and log in here off screen. And password.
Would you characterize much of this curriculum? In college, I did what's a microcontroller in the mechatronics class, and now I teach college courses. And so I take all that, and then robotics with the robot. So would you say a lot of this is that curriculum adapted to the microbit?
Well, it's a little more in depth. Did you say you did the basic stamp?
Yeah, I did basic stamp in a college class.
I see.
And
Did you
now
do
I teach it.
what's?
Go ahead.
Sorry, go ahead.
And so now I teach it in college, but I do when I did it and what I do now, it's what's a microcontroller and also robotics with the Bobot. But now we do everything on the Propeller One stuff with the activity bot.
Okay. So this is a little bit more circuit centric. There's more math and more measuring equipment examples used here.
Cool.
Well, I'm a lot older than most of you, because I'm 76. My very first basic stamp was the stamp bug from Milford Instruments. And I've been making parallax products ever since then. So I've worked with every microcontroller you make.
Oh, that's fantastic. Well, this will be a new one for you.
Not the microbit.
Yeah, but this I think well, hopefully it'll
before you guys picked it up.
Well, hopefully there will be some eye-opening new uses.
Oh yeah, I hope so.
Yeah, me too. Pardon me a second here.
Yeah, Ricky, at the UW, we used the basic stamp
Okay.
in the engineering course there.
That was my introduction at Michigan State, was that basic stamp. And then when I moved, I wanted to move because it's like, college students doing basic. So then the propeller and the multi-core, I found more appealing. But it is foundational, and it's a good thing for mechanical, right, who has very little electrical and circuits background. It's a great on-ramp.
Yeah, well, this was for a degree in electrical engineering.
Nice.
All right. For some reason, I'm not able to log in, and I'm not going to take the time to redo my password right now. So what I will do is move that demo to Wednesday. And so we'll just take a quick look at how you can log in and access the assessment material by going to learn.parallax.com, clicking educators, and then following the What's a Microcontroller with Python in the microbit link. Okay, so we have the student workbook, and then we have the educators resources. And then one other thing I wanted to talk about was how to purchase both the kits that we're working with today and the kits that we any other microbit related kits. And so going to parallax.com, and then there's a shop link. And when you follow it, you can, for example, I'll just go ahead and open the Cyberbot and the microbit. And I think those are the two main ones. Did everybody get their their step counter working, by the way? Okay, I've got some nods, some thumbs up. All right, just jump in if you couldn't get it going. Let's see here. So, so here is all things microbit. And so here's an example of what's a microcontroller with Python and the microbit. And this is the 12 pack. And so you can purchase 12 of them. And then down below, so here is a microbit club bundle. That's 10 microbits if you are just need to get microbits. Here is the individual what's a microcontroller with Python and the microbit kit. And so this is a good starting point. We even, if you have a bunch of microbits, we even have a version that doesn't have a microbit and we charge less for it. So this page is good for shopping. If there's anything you need to purchase for your classroom, there's a direct link. And then also there is an all things Cyberbot robot page, which has purchasing options for the Cyberbot robot. And if you have any questions, you can always email me directly or education@parallax.com, especially if you're trying to figure out, hey, there's something that I need to purchase, but I'm not sure whether I should get this or that. And
we have a couple who are requesting login to the educator only access. And I wanted, since we're getting several questions coming up, I will be sending a link with instructions to everyone, and logging in will be part of your homework at some point this week.
thank you, Stephanie.
You're welcome.
Yes, we'll get you all logged in. Okay. So with all that, then a real quick review of the pre-workshop homework. So we made sure that our microbit could receive a program and could also communicate through the serial terminal. We did a how to save a script, and then we did some real basics, communication, recollection, calculation, decision, and repetition were the subjects that I had you just try some select pieces of. And then we also experimented with the Cyberscope just a little bit, just to make sure it would display. And so what I wanted to do briefly was summarize. Oh, yes, go ahead.
On the microbit, is there any way to clear the screen? Just clear it? You're not gonna
You mean clear the,
just want to clear it.
are we talking about the LED display or this screen?
That screen.
Okay, there is. I'm going to have to search for that. It's an escape code.
Oh, okay.
Let's see if I happen to get lucky on Google. Yeah, I'm not seeing it. I found it at one point. It's an escape code from the old VT100 terminals, actually.
Oh.
Yeah, let me. I'm just gonna Andy find CLS escape code. Okay, I put a reminder for myself in the chat.
And is there I think that MicroPython like reference book or library?
Okay, so there's, yes. So the question is there a MicroPython reference book? One of the best things to do or one of the ones I recommend for the students is you can, in your Python editor, you can click help and select documentation.
Okay, thank you.
And this documentation serves as both a quick Python tutorial that you can use as additional material with what you looked at on the homework. And then it also has, it's probably hard to see here. Let's see if we can zoom in on it. It also has an API reference. And so, for example, we can look at the image API reference, and it will explain how how to create your own images. Let's see here. There's even stuff like UART for those of you doing serial communication with peripheral devices. NeoPixel is kind of cool. I2C, let's see, let's try buttons as a more simple one. And so, so this is good documentation, but then up above it, there are tutorials. And so these are things that the students can try. So for example, here, instead of just really focusing on image, you get an example program on how to display various images. You actually get several example scripts.
Thank you.
You are welcome. Okay, and let's see. Yes. So we talked about really the basics of scripting. And so just to summarize the homework, what I did was put all those little pieces in one monster program that we'll have you try out. Paste. Okay, so there it is in the chat.
You have a hand up, Andy.
Okay.
Oh, no, that was me. You already answered.
Oh,
Okay.
Is that
Thanks, Ricky. So remember Control A, or if you have a Mac, Command A, and then Command V or Control V to paste over whatever you had in there. And then for this one, what I did also was I changed it from displaying on the matrix display to print statements, just to make it go quicker. So we can flash this and then click Open Serial, but it's all the same concepts that you hit in the tutorials. And so it says press enter to continue, and I should actually close this and just to help clarify some things, I'll paste the code so that we've got it next to the okay, so yeah, I'm always choosing not now to stay in the V2 editor. So that's python.microbit.org/v/2. And I'm going to paste the code in on the left and then zoom in on it a little bit. And then we'll run it on the right here, just to talk briefly about some of the things. So here we have input, press enter to continue. So it's going to wait until I press enter. And then when it does, it's going to demonstrate what you tried in the remember part. And please chime in with any questions if you're new to the microbit and MicroPython especially. So what it did here was it set 4 different kinds of variables, or 3 different kinds of variables into 4 different variable values. And then the print statement displayed them. So that's basically store and retrieve data or recollection. And then we've got our next enter here. And after I press it, now A was 2 and B was 5. So hopefully C is going to be 7 when I press enter. Good. And then next up, we have the decisions. And so since A is 2, it's not greater than B. So it'll jump down to here and print that B is greater since it's 5. They're not equal either. And so this is an example of a yes question.
Is there a difference? I know some things have single quotes and some things have double quotes, like the input versus the print.
Yeah. So
Is it like string versus character?
no, what it is they're all strings, and strings have many different forms. You can even make a block string by using 3 apostrophes like that. See how it changed the color of all of this? So
Mhm.
that's a string including carriage returns. And so basically, the one thing though is that if you wanted to print a single apostrophe, you would need to enclose it in double apostrophes
Mhm.
like that. I believe you can also do a backslash and then a normal apostrophe. That should also display for you. And there is an entire chapter in the cybersecurity stuff that I'll paste in because strings in MicroPython are pretty amazing. Learn.parallax.com, and we'll go to Cyberbot.
Or cybersecurity is right next to it.
Oh, sorry, missed it. And then strings and characters primer. Actually, I'll start with the Cyberbot since that's got a superset of all that. Paste that in. And then the strings and characters primer. Copy the link. Paste that in for you. And then, so here we are. And you can, strings have built-in features. They're actually objects in Python. And so you can say stuff like, my string dot find. And so this talks, so here we have talking about the way to set up strings with apostrophes and our backslashes and how to name a string and print it, about ASCII characters that appear inside strings. Then there are things like, well, gee, you can use the built-in functions of a string to convert a bunch of digits to actual numbers to do math with them. So it turns out that you can add two strings and it'll just tack them against each other, but you can also convert them to numeric values, which I believe is going to be here. Now, this is indexing. And so for example, there are functions for for giving you an ASCII character or changing a number to an ASCII character. You can get the length of a string. You can convert something like an integer value to a string. You can also take a string that contains the characters that represent an integer value and use int to change it to a value that can be stored and used in math. And boy, there's a lot more cool stuff you can do with strings, including make a string something that's executable and runs inside a script, which is kind of dangerous, actually. If from the
security subject.
Yes.
We have a question about the code you were working with there.
Yes, back to that.
And
okay.
It is, what code gets it to wait until you press enter?
That is the input statement. That's the code that gets it to wait until you press enter. And you can, if you can say text equals, and then I could type in some text and press enter, and it would get stored in the text variable. And I could even say int of text like that and convert the text to a number. And those are things, again, that you'll see in other tutorials, specifically the strings primer that we just looked at.
This is very similar to MATLAB, some of these functionality.
Oh, that's interesting. I didn't realize MATLAB was so Python-esque.
Yeah, because it has an input command that waits for it, and then you can store this stuff.
Ah, I see. Okay. Yeah, because I remember it being more C-like, but then again, I only played with it in the 90s. At any rate, back to, let's see, so decisions. So we want to see B is greater. There it is. And then repetition. So the first repetition is to count to 10. And then after that, because this n only holds its value while it's inside here, I could have declared n out here and then done something with it. So I'm actually now saying n equals 10 so that it'll continue counting in an endless loop. And then there we go. And so one thing I want to draw your attention to if you're new to Python, and that is that if you want to do a group of statements using if or while or for, make sure to put them below and indented, because the next thing that's below but not indented comes after it's finished that group of statements. Pardon me, that group of statements. So that's mainly what I wanted to say about Python for all of you who are new to it. But I also want to really emphasize that if we go back to the Python, what's a microcontroller stuff, there is this writing microbits programs chapter. You did excerpts of it, but there's a lot more material here. So if you're new to MicroPython and you're feeling unsure about it, go through this step by step. Basically, set it just like I have it set up right here, and then read the explanation, follow the checklist instructions. They're going to tell you to enter this code, and in order to learn it the best, be it for your students or yourself, the best thing to do is to actually hand enter. So say from microbit import star a equals 89, and just keep on going. And that will, by doing that, it just makes it occupies more neural pathways. It makes a stronger impression both for yourself and for students. So if you can get them to do that, that's a really good thing. Otherwise, we do have some try this and your turn stuff. Like if I scroll down to the bottom, it's not on this page, but there's a lot of times where the answer is reserved for the educators only. And so that way the students will have to think about what they're doing and put their hands on the keyboard. But the more you put your hands on the keyboard, the better, up until a point. Sometimes once you're pretty good at coding, a large code example, it's not really time effective to enter the whole thing in. But when you're first getting started, yeah, that's a really important habit to develop. And now on to the hands-on. We have 10 minutes before the break, so let's see how far we can get with this. We already talked about the Learn site, and within the Learn site, the What's a Microcontroller with Python and the Microbit webbook. The first chapter in that is setup and testing for the microbit. I'll go ahead and one more time do this from the beginning. Okay, so we'll go to learn.parallax.com. And then what's a microcontroller with the microbit? Here's the book cover. And we're going to go into breadboards. Oh, you know what? I forgot to mention about saving a script. Okay, so let's say we have a large script. We can name it large script by typing it into the script name field up here, and then hit load save and download project hex. Okay, now that I've done that, I could actually refresh this and nuke my large script and start writing another script. So here I am writing another script, and then I want to open my previous script. Well, to do that, the quick way is to just drag and drop the large script back onto your editor. I'm going to do that, though, from the downloads. So you can open your file browser here. And then here's large script So here's large script.hex. Did that zoom in for everybody? Can I get,
Yeah,
okay,
good.
thank you. Thank you for the confirmation. My Mac stopped doing that recently, which is one of the reasons I'm trying out this PC.
Can I,
Go
add
ahead.
what's, two things. If I'm in a classroom and I'm using the web base, does it auto save by anything? Because it scared me when you hit refresh. I can imagine the students losing all their stuff. Is there an auto save feature?
There is not an autosave feature, but that's one of the reasons why I emphasized to hit
Save.
the load save button
Right.
and select download project hex.
Second question, I'm assuming the .py would be text-based and the other one's just hexadecimal code?
Well, yeah, and the hex file has a couple of advantages. First of all, some districts prevent Python scripts from being downloaded because Python scripts for computers can be executable and malicious.
Okay.
The second thing is that sometimes, like with the Cyberbot and the Cyberscope, we have down in our files, we have a main file, but then we have an additional file, like maybe cyberscope.py or cyberbot.py added down here. And the cool thing is, if you save it with it added to the project, then when you open the hex file, it's still there. If you download a Python file, you'll have to manually go and find, and download and find your that extra Python file that has functions and methods you can call. Whereas if you download it as a hex, it'll just be there for you next time you open it.
So if I instruct students to turn in the hex file with their homework, and I can usually look at some type of text and make sure they're not cheating.
Oh, absolutely. And so all you have to do is when they turn it in, you just take the hex file and drag and drop it into. So again, so you want to have them hit load save and then, and then use download project hex to save it, and then they can submit it to you. And then when you get it, you might just open up your editor and it'll look like this with just the default script. And then you can take the hex file that they sent you and just drag it and drop it in the editor. And there it is. Alternatively, you can hit load save, and then the or browse for file link is your open link. And so you can go and get it from there too. So like I'll open try Cyberscope this time.
Thank you.
And since I opened try Cyberscope, now we can see that there's a multimeter.py extra module in here that that has functions that are called within this demonstration file. So like, see here, plot is one of those that is not defined in this script. It's defined in that little plugin, which is called multimeter.py right here. Okay, so that's another thing that, again, that comes with a hex file. Okay, now we have 4 minutes. I'd like to at least put our hands on some stuff here. So I will switch over to the camera. All right, so we have our microbit already out, but we also have a nice box of goodies, which is the What's a Microcontroller That's Wham with Python in the microbit. And so you had your microbit in there, which I've already taken out and connected, and there was also the USB cable. And so what's left in here is going to be an adapter in a large silver bag. So we'll take that out, and we'll take the breadboard out. And we also want to go way to the bottom and grab the other silver bag that's labeled 5723250. It's got all of our electrical and electronic parts. And sorry, the reflections are pretty bad. There we go. I think those three things. And then while we're in there, let's grab a red and a black alligator clip. I think that's pretty much all we'll need for today. So here we have our alligator clips and the two bags, and we don't even need the microbit for the rest of the day. Although later on, we will be going back in here, or actually, no, we might, depending on how the day goes, we might measure the voltage across these batteries. We'll see. So keep that on hand. But primarily we're going to use these things. And so let's go ahead and take them all out of the, including the breadboard. So let's go ahead and take those all out of their bags. You'll need a bowl for your small electronic parts. Nice and neatly sorted. And then we'll get our little adapter out. So this will eventually be plugged into the breadboard, and then we'll plug the microbit into it. And then we'll also use some of these jumper wires right here to set up our breadboard so we can do prototyping with it. But that is all going to come after the break. Let's take a 7-minute break and pause the recording. I'll stick around for anybody who's got questions. But if you need to go grab a glass of water, use the restroom, talk with kids, whatever, go ahead and do that. And we'll see you back at 7 past the hour. All right. Welcome back, everyone. It is now 7 past the hour, and we're going to continue with the hands-on portion of this workshop. Let's see here. So we have all our goodies out here. And first thing is, let's go ahead and disconnect our microbit from the serial cable because we don't want power while we're putting this all together. Next up, we'll be starting with just the breadboard, the adapter, and the microbit. So make sure to have those out. And then this is from the breadboard setup and testing chapter. So again, here we are in the web book. These are the prereqs, including connecting your microbit, saving and opening a script, programming basics, and then using the terminal to communicate with the microbit. And then after that, we have the breadboard setup and testing chapter. So we're moving along at a pretty fair clip. And so here we are with an example of something that's in the chapter, and we always list what you'll need, stuff to complete first, and then we have the contents along the left. And you can also navigate by these little next and previous pages. So previous page, scroll to the bottom, next page. And then you can go either direction once you're past the start. So, your system is going to look like this once we're all done. The tutorials try to take a number of concepts and make them very visually clear to students. And we have an automated GIF file, an automated .gif file, animated, pardon me, GIF file that keeps on replaying, but it's good for students often to go step by step. And so we also have a MP4 file version of it that they can open in another screen. And then you can actually play it. And for example, there can be a discussion in class as you're playing these and talking about, hey, this is the terminal strip, and there's another terminal strip, and then each terminal strip has, and you can rewind here, which is also a really nice feature. Each terminal strip has column letters as well as row numbers. And then there's the "You Sunk My Battleship" kind of column and row coordinates. And so here we have row 16 and column G, and we can even call that socket G, 16. Then it also introduces bus strips, which are the vertical strips that we use to connect power and keep it close to various parts of the breadboard. So just wanted to let you know that we have animated GIF files and MP4 files salted through this to help get the idea across. And so here we have, for example, those 3 items that I set aside: the microbit, the adapter, and the breadboard. And then the next thing we have, and let's look at this one carefully. Okay, so the first thing we'll have you do is, and go ahead and follow along right now. The first thing we'll have you do is insert the microbit into the adapter.
I have a question. We should have this unplugged at this time, or can it stay
Yes.
plugged?
No, go ahead and unplug the microbit.
Okay.
And you can also take off the little piece of foam that's under the adapter. Make sure that the microbit is buttons and lights side up. It won't hurt it if you do it the other way. In fact, it'll actually still work. But it's better to have it this way. Make sure to insert it so there's less than half a circle left on these little circles on the microbit's edge connector. So like so. Next up, we want to get our breadboard situated so that the smaller numbers are on the top, the larger numbers are on the bottom, and everything's readable and not upside down. So you see how 1 is on the top there, 1, 2, 3. So make sure to orient your breadboard so that 1 is on the top, and then 26 through 30 is going to be on the bottom. Next up, we want to get the pins started into the holes on the breadboard. So basically, you're going to line up the P0 pin with A30. See if there's a close-up of that. So we're making it translucent, and now you can see that there's A30 is the bottommost pin, and 2 rows up in the vertical bus strip, there's going to be a couple of pins. And so you want to make sure that you've got your microbit set up like that.
Is there a particular reason that you line it to the bottom?
Oh yeah, absolutely.
I see that there's power things going into the bus.
Yes.
If we moved it away from 30 in the middle, for example, does that affect anything?
Well, the effect it's going to have is that you'll be out of sync with any of the circuit diagrams. One place where I could see that as an advantage is if you want your students to actually be working from schematics.
Right.
But aside from that, yeah, we try to keep it as shown just to stay in sync with the diagrams that are coming up.
Even college kids love the pictures. That's always a fight. Don't look at the pictures.
Yes, and they love them too much sometimes, and then they
Yeah.
like don't pay close enough attention to schematics. But yeah, it's we try to get it for everybody. So see, we even have a close up now that bottom right pin in the edge connector is going to be lined up with socket A30. And then as long as you've got it lined up with socket A30, all the rest should follow. Once you've got it properly lined up, then you're going to need to press it so that those pins sink all the way up to the little plastic edges. Oops, back it up a little further. Okay, so the pins are going to go in all the way up to the plastic, the little plastic pieces that hold them together. Boom. And you're going to probably need to press hard. I recommend putting a thumb. Stop. Yeah, I recommend putting a thumb about here and another one about there and pressing down very firmly. I'll show you on mine. Okay, so here we go. So I'm lining up that bottom pin in A30, and then everything else follows. And then make sure that your pins are lined up like so. Hopefully that's coming through okay on your screens with the pairs of pins in the bus strip, and then the other pins in the terminal strip. And then once you've got it like that, go ahead and press very firmly, and then they'll sink all the way in. And it should look like that when you're done. Okay, so can I get some thumbs up if you've got it going? Thank you very much. Looking good. Great job, everyone.
Andy, have you ever had any students or anyone having problems with bending those pins when they're pushing that down? Like for me, it's like you said, you got to press firmly. I'm just wondering if you get younger students trying to put those in. Have you ever had any problems with that?
Not so far, but I'm sure it could happen. Those pins are fairly sturdy, so a needle nose pliers can be used to straighten them out. It's bent, yes. Broken, no. Not so far anyway. Fingers crossed.
If you get it all lined up and you put a thumb on each end of the thing and then rock it back and forth down, it'll ease it in and you won't get the bent pins.
Good deal. Thank you. Yep.
Anyway.
Yeah. I did as much as I could to make sure that it's student proof, but yeah, I think just encouraging students to put their thumbs as Carol described is gonna really help. Okay, so once we've got that together, then we're going to start talking about electrical connections with a breadboard. And so, so this is the cover and then of the activity. And here we have another instructional aid that is going to explain how the rows of 5 sockets are all electrically interconnected. And there's some text that goes along with this. And so one of the things that we do is show students how to pick a row of 5 and they can plug wires into it and then it'll show them as connected, and then a separate row of 5. And now the important distinction is because the rule is rows of 5, the one wire above and below each other are not connected. But if you add another wire to that row, you've got those two wires connected, but the above and below are not connected. And then the two wires in the same row are connected. And you can also switch over, even though it's on the same row here. Yeah, it's again, re-emphasizing the row of 5 rule. And then also that you can use a jumper wire to extend a row of 5 to basically make it a row of 8. So if you add a jumper wire to connect 2 rows of 5 electrically, then you have 8 sockets left. So you could connect up to 8 things. And of course, you can expand that further as needed. Let's see here. So what we're going to do is bear with me a second. Okay, so this is a continuity activity. And we're going to do this before building. Well, let's just go ahead and do the continuity testing activity. You'll need these parts. The 3-pin headers are going to be in that bag of small parts that hopefully we have emptied into a bowl. So the 3-pin headers look like this. Maybe if there we go. So that is one of the 3-pin headers from the kit. And so you will need a pair of 3-pin headers, the red and the black alligator clips, 1 red jumper wire, 2 black jumper wires, and a blue. Though they're all made of the same metal, they all conduct electricity the same way. But it is helpful for identification. So go ahead and grab those parts and then give me a thumbs up once you've got them all set aside. Thank you. Seeing some thumbs up. Good job, everyone. I might need to catch up with you all. Okay, let's see. All right, I think I'm good. So let's go to the circuit. All right, so go ahead and put this together. I'll paste you this link in case you want to bring it up in your browser. Playing it again here. So the 3-pin headers need to go next to P2 and P0 on the adapter, and put them in the sockets closest to the well that separates the two rows of 5. And then put the black and red wires in your alligator clips and plug them into different rows. And I'll pause it on that one while I put it together myself. Okay, so 3-pin headers inserted all the way into the sockets next to the P2 and P0 adapter pins. And then red alligator clip on the P2. Try to grab as many of those pins as you can with the alligator clip. Black alligator clip on P0.
Andy, I have a question.
Go ahead.
So I know that it says not to let the alligator clips touch each other. So could you move it up to like P3 or P4?
Well, what you
or-
can do instead is you can move it up if you want. So it's not going to hurt anything if they do touch each other. And the insulation pretty much keeps them apart. I mean,
Okay.
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 But if it becomes an issue, I can't really foresee that it would, but
Okay.
what you can do is you can take a jumper wire and actually jumper up to something empty up here, and then put the 3-pin header in there too. So that's a way to. Sorry, go ahead.
No, I just thought that there's something special about P2.
Well, there is, which is why you would be jumpering if you wanted to get that. It makes it more convenient to follow the tutorials that,
Okay.
so you don't have to change the code every time. But you could, for example, jumper P2 up to a row above the adapter, and then stick the 3-pin header in up here, and then you could actually, clip onto the 3-pin header up there. That's doable.
Okay.
Or just let them be like that, because it's not really going to hurt anything if they touch.
Okay. Thanks.
Aside from that, you'll get incorrect measurements. Okay, so have we got our board built up? Can I get some thumbs up from everyone? All right, looking good. Give me a shout out if you need a couple more, seconds or minutes. Otherwise, we'll go ahead and continue. I guess I still need to catch up with you. Let's see, that was in 16 and 17. Whoops. Yeah. So 17 here, and then 16 here. So then the question to pose the students would be, all right, are those 2 wires connected now that I have one plugged into 16 and one into 17? And the answer should be no. And by the way, now that you've got this set up, you can go ahead and reconnect your microbits USB. All right, there we go. Okay, next up, we're going to, and incidentally, in addition to the video, we've got red checklist instructions. So those are the action items that the students should really follow. And then this is hopefully a very useful visual aid for these instructions.
We have a request to please show the 16 and 17 one more time.
Okay. Let's see, I think I had, there we go. Is that visible?
Yes.
Great. So red alligator clip, 3-pin header, P2, black alligator clip, 3-pin header, P0. On the other end, black alligator clip, wire, row 17, red alligator clip, wire, row 16. And next up is the script. So I'm going to paste you this page because what you're going to need to do is right click and select Save Link As. And then it'll save continuity tester.hex. And what that'll do is it'll save us having to add the Cyberscope module to the script. So, so I'll go ahead and paste this page and we'll have all of you grab that continuity tester.hex script by, again, right clicking and selecting Save Link As. Now, once you've done that, you can go over to, see, let me bring up Learn. Okay, so again, I'm going to download continuity tester.hex and save it. And then it should appear in that little bar below, below your web page. And you can actually drag and drop that into your Python editor to open it. And again, for Ricky, when I hit load save and then hit show files, see how multimeter.py is in there?
Mm-hmm.
So that's the advantage of the hex file, is that it is that additional resources can be stored inside it, whereas it's just text when you're downloading a .py file. And then you actually have to go in and hit add file and have downloaded the multimeter.py from somewhere. So so it's just a lot easier with the hex file. And then make sure your microbit's plugged in, hit connect, select your microbit, and hit flash. And I don't remember if there's, I don't think we need open serial for this.
I got beeps and a check mark in Zoom.
Yeah. Oh, well, if
Yours
you
is
have
very
beeps,
different.
if you have beeps and a check mark, it means you're connected.
Right. So when
so-
I connect, I get that. When I disconnect, it's a 0.
Ah, good. Yeah. So basically right now there should be a circle with a slash through it if you're on row 17 and 16. But if you unplug, say the black lead from 17 and plug it into 16, then yeah, you should get beeps and a check mark. And then if you let go, you'll get nothing. And you can even just connect the two probes together and you get beeps and a check mark. So that's only when we're either touching the probes together or connecting them on the breadboard. And so students are guided through experimenting with that to see what's connected. And then additionally, you can try out, say, the sockets along this blue vertical line here. So if you plug them into anywhere next to that blue vertical line, they're connected and you get the check mark and the beep. But if you plug one into the socket next to the red line and another into the socket next to the blue line, then they're not connected again. But if you switch over so that they're both next to the red line, doesn't matter where you are vertically, they will be connected. Just as if you have a row of 5, doesn't matter which of those 5 sockets you go to, it'll always connect. But if you're even up by one row, it's not connected.
So 2 questions.
Yeah.
We have time. Number one, I know it's not scrolling, but it looks like it's scrolling on the camera. Am I looking
Yeah.
at code? It's running through the code and we can pick it up with the refresh rate of the camera.
Yeah, it's the refresh rate of the camera. I'll try to do something about that. I've had, see, the thing is that there's a brightness setting in the microbit. And so it's actually PWM flashing those lights on and off.
And we can pick that up. That's pretty cool. Right.
Yeah, it is. I'm glad it's displaying somewhat. There have been previous cameras I've used where it didn't display at all.
So
Oh,
Yes.
sorry.
behind the scene, is one pin set to 0 ground and the other one set to high. Is that what's going on with 0 and 2?
Behind the scenes, it's testing the voltage at P2 and the voltage at P0. And it's
Mhm.
saying if they're really close, they're probably connected.
Right.
And then inside the microbit, there's also resistors that are pulling the voltage, I believe, up. Oh boy, I don't remember. I'm going to have to take a look at that. Yeah, can we save that one for after the session? We've got some discussion not recorded after the session, and I can try to refresh my memory on what I did to make that work.
No problem.
Okay. But yeah, it's the voltage is, I'm almost positive that the voltage right now is being pulled in a particular direction, and possibly even one pulled up and one pulled down.
That's what I see.
Yeah, I apologize. I don't remember. Okay.
Andy,
Yes.
this might seem a stupid question because I don't see it on this editor like it is on most Python editors. Where's the run symbol? I mean, how do you get the script to?
The
Wait,
the flash button is.
No, I already flashed it.
Yeah.
It's in the microbit, and it's showing me the proper symbol that the continuity tester is the program I have in my microbit. But how do you get the code to actually run, to activate?
Flash is load and run. So all you need to do is connect the two probes together, and it'll change to a check mark, and then take them apart, and it should be a circle with a slash through it. So flash again is load and run.
Oh, I see. It's on. Yep, I got it. It's on
Perfect.
the microbit screen, not the display.
Yes.
Okay, I was looking at the wrong thing.
Yeah. I don't think it's displaying anything in the serial port.
Okay,
Just
0 or check.
so let's see. We're getting some.
We have a hand up.
Okay, go ahead.
We have Eric. Eric?
Yeah, you're very distorted.
I'm sorry, Eric, we can't understand you. Can you type your question into the chat window?
And also, can you mute yourself? I think we've got some background coming from you too.
Yeah.
Okay, well, let me know when the question comes through on the chat, Stephanie.
Okay.
Let's see here. So that is continuity testing and just learning about making connections on a breadboard. And just so you know, there's video clips showing what to expect when you're connected and not connected. And then there's trying more different tests. In fact, we get to try all the different tests that were shown earlier in the video, where you're on different rows and then on the same row. And then eventually it'll come around to even jumpering the two rows together. So now we're on the same row on the other side, but then once it's separated by the well, we're not connected. So it goes through all that. And the how it works, sadly, is not going to tell us what we need to know, or what Ricky asked about the about how I set up the measurements. I need to look inside the library for the cyberscope. I guess that is a pretty good side topic. So let's, I'll just real quick, see if I can do this quickly here. So here's the script. I'm going to open the script in the V3 editor. Okay, so python.microbit.org/v/3.
We do have Eric's question.
Oh, good. Let's take a look. Notice when I connect the black terminal to the negative bus, where the negative of the microbit is, it beeps. That doesn't happen with the red cable. Nice catch. You found an interesting thing. I'm going to have to, okay, so what he's saying is that, I think what you're saying, Eric, is, well, why would we be getting beeping there? So you're saying that, let's see, connect the black terminal to the negative bus. Oh, where the negative of the microbit is. So you're talking up here. Yeah, that'll do it. So that is something that a real continuity tester would not do for you. And I'm going to have to add that to as a comment in the tutorial, that essentially when you take the ground lead of the continuity tester and plug it into this negative, this row is the negative terminal of the microbit supply here. And so it kind of fakes you out and indicates continuity, even though it's really not the case. Very good point. That's kind of a unintended consequence of the way I set up the continuity tester. These are not meant to be, measuring equipment. It's a $20 microbit, so it's not like a high-end fluke meter, for example. But it is intended to, for the most part, demonstrate how all this stuff works. Let's see here, set power for circuits. So now we're going to add these wires right here. Let's see here. So we're going to get 2 more red wires and 2 more black wires. And here's a close-up on how they're supposed to be connected. So we want to use the black wires to connect a socket next to the blue line from the left to the center, and then the blue line from the center to the right, next to the blue line sockets. And then we want to do 1 red jumper wire from the red center to the red right side, and then 1 from the 3V row, that's row 11, to one of the red sockets. No, that's too large. Almost. There. So go ahead and add those 4 wires.
Andy,
Yes.
I happen to have a couple of the old connectors that are on the blue boards made by Parallax.
Yeah, so those need to go on the other side.
Oh, okay, because I noticed the pins were different.
Yes, yeah, those go, the black one connects to the left side. You want to connect the blue older, if your board, if the color of this board is blue, which none of you are going to have blue boards except for Carol. And for Carol, what you'll need to do is just mirror image it and connect it over here on the right.
Okay.
Do you have any of the newer black?
Yeah, I'm using a newer black. for-
Okay, good.
Yeah, no, I got the newer black. I noticed the pins were different is why I didn't use my older blue ones.
Yeah. Good, because that could get a little bit confusing. We only ran a few of those original blue ones. Those might be collectible someday. As is your stamp bug and some of the other items you have.
Well, I gave the stamp bug to Ken, but I do
Oh,
one of almost everything you've ever sold in robotics, at least.
wow.
I've still got the old rulers too.
Ah, yes, the engineer's wand, I think they called it. No, mine are out of reach. Okay, so hopefully your setup looks something like this. Where we have the black wire. Let's see, maybe I'll, hey. So Carol, are you talking about these rulers? The inventor's wand.
Yeah, I have about 3 of them left.
Yeah, I think I have 2 left. Anyhow, so let's see here. So make sure that your blue socket to blue socket, and then blue socket to blue socket, red socket to red socket, and then 3V row to red socket. And with that, what we'll do is go to the script. So you're going to download measure volts from the, and again, that's right click, save link as. So I'm pasting that into the chat. And then we'll download measure volts. Right click, save link as, save it, and then drag and drop it into the editor, either from your downloads folder in a file browser or just where it appears in the bottom corner of your Learn Site page. Then we'll go ahead and run it. So that's going to be make sure you're connected and then hit flash. And for this one, we're going to open the terminal. And it's probably, if you're not connected, it's probably going to show a low voltage. And so what we need to do next is, and I'm kind of paraphrasing for the the chapter here is we want to test and make sure that we've got 3 volts across our red and blue, 3.3 volts across the red and the blue socket. So connect the red or the black probe to a blue socket on the right and the red probe to a red socket on the right hand side.
Andy, we have a request from a couple minutes ago
Uh-huh.
from Usha. I am so new to all this. Could you please show me the red plus or what it means?
Okay. So the see the blue stripe here that's vertical on your board? Any socket next to that blue stripe should be essentially ground or 0 volts. And so we're plugging our black P0 probe into any socket next to the blue stripe at the far right of our breadboard. And then the red socket, after getting the wires as so, should be connected to the red sockets by the red stripe. Those are all interconnected. And the electrical connections that we've created here are basically giving us this 3 volts of power on any of the, or on the two, the center and the right bus strip. So the idea is to test, to probe the red and blue over here and verify that you've got about 3.3 volts. And then also probe the red and blue in the center and verify that you've also got 3.3 volts. And for extra credit, you can grab a battery out of your Microbit Go box and measure it by connecting the black probe to the negative or flat end of the battery and connecting the red probe to the positive end that has a bump. And we'll notice that we're about 1.53 volts, which is an okay voltage for a brand new battery. It'll go up to, some batteries will be hot enough to be slightly over 1.6 volts. 1.65 is the hottest I've seen.
Randy's reporting getting a total of 3.28.
3.28, yeah, that's great. So that's across the that's across those rows there, right? Or I mean, that's across that's between the sockets that are connected by a socket to the right of a blue stripe and a socket to the left of a red stripe.
Yep, getting a thumbs up.
Perfect. Perfect. So what we've done here is we've set up our prototyping system and gosh, there's 7 minutes left. Well, yeah, what the heck? Let's get our light built. I'm going to skip ahead here a little bit. First breadboard circuit.
So this uses, I'm assuming because of the 3.3 TTL logic is what this board chooses. Is that accurate?
It's 3 point, well, okay. So the question is, what's the difference between a high and a low signal on the microbit? And let's see if I can remember this. I want to say that the microbit will give you a 0 if you're below about 1/3 of 3. If you're like 1.1 volts or below, the microbit will read a 0. If you apply 2.2 volts or above, it'll switch to a 1. So there's hysteresis in there. And anybody who's kind of new, don't worry about that question. We'll visit it in more detail later. Let's build this circuit. So find a resistor that has a has the stripes red, red, brown, gold. And that a resistor looks like this. We're going to build this on the right side, and we're going to connect the resistor to a socket by the red stripe, row 16. We'll plug the longer of the two light emitting diode pins. And again, I just skipped ahead abruptly because we've only got a few minutes left. So I'd like to at least turn on a light and measure the voltages on it. And then we'll connect a black wire here from a blue socket to row 16. Just like in the picture. Let me see if I can zoom this a little bit. Is that clear enough, everyone? Excellent. And for anybody, if you need to zoom in on it on your computer, I'm putting it in the chat as well. Okay, so let's go ahead and build that up. And remember, the long LED pin should be towards the left here, on the left set of 5 sockets. And then the shorter pin should be on the right. Make sure to get everything on the same row, not above or below, because otherwise it won't work. Red, red, brown, gold is going to be the stripe colors on that resistor. It's the set of resistors that are taped together. Looks like this. So find these, grab one of those, and then you can plug it in with your light emitting diode. I'll go back to the image. Normally, I believe the instructions say to disconnect power, but don't worry about that. You're not going to hurt your microbit or anything else as you're making this circuit.
Then offline question would be, I'm looking for it, but I haven't found it. How much current can a particular pin?
Yeah, so microbit pins are particularly wimpy. They don't supply a lot of current. Let's see here. Let me see if I can find my calculator.
I see here 3 onboard peripheral. It says 90 milliamps or 300 milliamps max.
Okay, so when you're on the supply, just a second. When you're on the supply like this, yeah, the microbits regulator is 180 milliamps or something like that. I'll have to look that up. But if you're connected to a microbit I/O pin and you're programmatically turning the light on and off, then you only get like 2.7 or 2.8 volts if you load it with a light like this. Then it's about 1 volt across here, so it's 1.8 volts across the resistor, and then we'll use V equals IR.
All right, let's go. Ohm's law.
Yeah, that's coming up on coming up soon. 1.8 divided by 220 equals, yeah, so 0.8 milliamps seems to be about where an IO pin maxes out. 8.1 milliamps. Doesn't seem right. 1.8 over 220.
That's right.
Yeah, 8 milliamps seems a little bit strong. Huh. Well, that's pretty good.
And probably because green wouldn't be 1.8, it would be probably slightly higher, right? Like around 2 volts.
Oh, that's the problem. I got my voltages reversed. It's 2 volts
red
across the light. So basically it's going to be 0.8. Yeah. So about 3.6 milliamps. That's more reasonable as where it tops out current wise. For anybody who again is new to this, that question and answer is addressed I think on Wednesday. So we'll be talking about electrical properties like current and resistance. Let's see, it is now. We now have 1 minute left. Did everybody get their light to come on?
We have a couple people might need troubleshooting. Did you?
Okay, so
have some thumbs
real
up?
quick before we do that, then, for those of you who do have a green light, mine really is green. It's just hard to see.
We can see it.
There's, okay, so now if you go back to your voltmeter, you can probe across the whole thing
Nice.
from the red stripe on the left to the blue stripe on the right, and we'll see that it's applying 3.3 volts. Then you can probe the resistor and see that it's dropping about 1.3 volts, and then probe the light and see that it's dropping about 2 volts. And guess what? That's a demonstration of something called Kirchhoff's law, where basically if you have a series circuit where current is flowing through the circuit and everything's connected end to end, that the sum of the voltages on the parts, that being the resistor here with 1.32, and the LED with about 2 volts, just under 2 volts, you add those up and it's going to be 3.3 volts or 3.29, depending on the moment you test it. And so that's one of the things that is introduced in electrical measurements. And so I just wanted to have you try that out as a real measurement. And then again, also measuring across the battery is going to be a good measurement to take with about 1.58.
Did you write this code yourself, or is this a micro?
This is all, I think I wrote all of this.
Oh, pretty cool.
Thanks. And incidentally, one last thing, and then I'll show you the homework and let you go. Sorry, we're running over just a little. I'll try to minimize it. What you can do is you can actually change this device to cyberscope and then flash it again. So line 8, change the device to cyberscope and then flash it again. Now it's going to look way different now so this is the data that gets sent to the cyberscope. And so you can close serial and hit disconnect and then go to cyberscope.parallax.com. Cyberscope.parallax.com. I'll paste that in. And then hit the connect button. Now make sure to disconnect here and then go to cyberscope.parallax.com, hit connect, select your embed or microbit port, depending on what it shows. It'll either say embed serial or microbit or something like that. And when you hit connect, you'll actually have a real voltmeter display. And so you can go back and measure the battery and see the 1.5 something volts. And you can go back and measure the resistor and see the 1.3. Oh, I got my probes swapped, so it was negative 1.3. Now we got the 1.3 and the approximately 2.0 for the light. And the 3 volts from red to blue socket. Okay, so one last thing is that we're going to have some homework. And I need to figure out exactly what homework to send you. No, I think I know. Okay, so we're going to be connecting some push buttons and some lights to get us set up to mainly work with scripts as opposed to building and troubleshooting circuits. We'll have to do a little bit of troubleshooting. So ahead of time, this push button here, the legs come out the side. Make sure to orient it so that the legs are coming out the side, and then insert it into the breadboard so that it crosses the valley between the two sets of rows of 5 circuits. Here is the circuit we're going to have you build. I will email a link to you with this diagram, and probably a link to these 2 pages, how to do the push button and how to build all the circuits. And then here's a schematic of what it looks like. Those are also included. And so we'll do some applications and measurements with this. So that's going to be your homework. Keep an eye open for an email from, I think we'll have Stephanie send out the email on Wednesday. So we'll have you sign up for learn.parallax.com so you can access the teacher resources on Friday. Okay, so that's it for today. One last thing is, when you're done, unplug your USB cable from your computer so that your power is completely off. And if you took your batteries out from the, it's best to store these in a Ziploc baggie. Don't throw them in with your electrical parts, because you could end up inadvertently creating a circuit by doing that. Usually, like a standard plastic Ziploc bag is a good thing to store your batteries in, separate from everything else. Seal it off, and then you can drop it in with your circuit parts, but you don't want to drop it in if it's going to be able to touch any of the circuits. All right, so that's it for today. Keep an eye out for a homework email. I hope you all enjoyed that, and anybody can stick around to hang out afterwards for troubleshooting and also for questions and answers. I'll give troubleshooting priority though. So if you got stuck on anything, now is going to be a good time. I can also Zoom with you between now and Wednesday. So, so for those of you sticking around, we'll continue talking in a minute. For everybody else, this is the end of the recorded portion of the workshop. Thanks a lot for coming, and we'll see you Wednesday, same time, 3 p.m. Pacific, same Zoom link as you used to get to this one. Thanks for coming, everyone, and let's end the recording.